Maximization of entropy. An object of mass m1, specific heat c1 and temperature t1 is placed in contact with the second object of mass m2, specific heat c2 and temperature t2, which is greater than t1. As a result, the temperature of the first object increases to T and the temperature of the second object decreases to T prime. Part A showed that the entropy increase of the system is delta S equals m1 c1 natural logarithm T over T1 plus m2 c2 natural logarithm T prime over T2, and show that energy conservation requires that m1 c1 T minus T1 is m2 c2 T2 minus T prime. Part B showed that the entropy change delta S considered as a function of T is a maximum if T is equal to T prime, which is just the condition of thermodynamic equilibrium. Part C discussed the result of Part B in terms of the idea of entropy as a measure of randomness. Okay, so let's start with Part A. So we're going to write the entropy change of the first object. The entropy change of the first object, delta S1, its temperature is changing from T1 to T, dq reversible divided by T. So it's being in contact with thermal reservoirs at temperatures T with ever increasing temperature between T1 and T in a reversible process. This is integral from T1 to T, M1 C1, let's make temperature a dummy variable, T double prime, divided by T double prime. So this will be my integration variable, and that will give me M1 C1 natural logarithm of T double prime evaluated between T and T1. This will be natural logarithm T divided by T1. The entropy change of the second object, delta S2, will be integral from its initial temperature T2 to its final temperature T prime, dq reversible divided by, so here I used T double prime, here I'm going to use also T double prime as the dummy variable. So this will be the integral from T2 over T2 to T prime, m2 c2 dt double prime divided by T double prime. The same story here, we have m2 c2 natural logarithm T prime over T2. T prime over T2. So if I calculate the total change in entropy, delta S, which is delta S1 plus delta S2, this will give me delta S equals M1 C1 natural logarithm T divided by T1 plus M2 C2 natural logarithm T prime divided by T2. All right. And I noticed that this is the answer I was looking for. M1 C1 natural logarithm T over T1 plus M2 C2 natural logarithm T prime over T2. Now, if I write the energy exchange between the two, the first object is absorbing energy M1 C1 delta T1, which is M1 C1 final temperature T, initial temperature T1. Second object is absorbing energy M2 C2 delta T2. This is M2 C2, its final temperature T prime minus initial temperature T2. And we should have Q1 equals minus Q2. Heat provided by second object must be equal to the heat added to the first object. So heat added to object 1 must be equal to heat released by object 2. And that gives me M1C1 T minus T1 must be equal to M2C2 T2 minus T prime. So that is the requirement of energy conservation. Let's compare this with this answer. M1C1T minus T1 is equal to M2C2 T2 minus T prime. So we have achieved the task. In part B, we're going to maximize the total entropy. So what I'm going to do is take this energy conservation equation divided by M2C2. I obtain M1C1 divided by M2C2 T minus T1 is equal to, and if I take T2 to the left hand side as minus T2 is equal to minus T prime. So therefore for T prime I can substitute T2 minus M1C1 divided by M2C2 T minus T1. So in other words, when I have T prime divided by T2, this is 1 minus M1C1 divided by M2C2 T minus T1 divided by T2. T minus T1 divided by T2. So if I go back to my entropy change, delta S, it was M1C1 natural logarithm T over T1 plus M2C2, it was natural logarithm T prime over T2. For T prime over T2, I'm substituting natural logarithm 1 minus M1C1 divided by M2C2 T over T2 minus T1 over T2. Okay, now I'm going to take the derivative of the entropy change with respect to temperature dt, d delta S dt, and set it equal to 0, so that I'm going to obtain the maximum in the entropy. So the first term, M1C1, we will have 1 over the inside of the natural logarithm, which is T1 divided by T, and the derivative of inside with respect to T is, the derivative of T over T1 with respect to T is 1 over T1. So these T1s will cancel. And as for the second term, I will have plus M2C2, derivative of inside with respect to T. You can see this comes from this term. So that will give me minus M1C1 divided by M2C2 1 over T2. That's the derivative with respect to temperature of inside. And then I have 1 over the inside, which is 1 minus M1C1 divided by M2C2 T over T2 minus T1 over T2 parentheses to the power minus 1. Okay, so having finished these derivatives here, here I want to note that M2C2 terms will also disappear, and I can rewrite my result as the following. The derivative of the entropy change delta S with respect to temperature is M1C1 divided by the temperature T, because I've gotten rid of the T1s here. And then I have minus M1 C1 divided by temperature T2. That is this term here. And then I have 1 over 1 minus M1 C1 divided by M2 C2 T over T2 minus T1 over T2 parentheses, and this should be equal to 0. So I can get rid of the M1 C1s. So I'm left with 1 over T here. And if I multiply this with to get the common denominator, I will have the first term 1 here multiplied by this term. So here I will have T2, and let's distribute it. This will be T2 minus T2 times M1 C1 M2 C2. So it's going to be T2 minus M1 C1 divided by M2 C2, and T over T2 multiplied by T2 gives me T, and then I will have two minus signs here. It's going to become a plus, so it's going to be plus M1 C1 over M2 C2. T2s will cancel. I will be left with T1. So that's this term when it goes upstairs. And then I have a minus T divided by the common denominator is set it equal to 0. So I can get rid of the common denominator because the numerator should be 0. So this gives me T2 plus M1 C1 over M2 C2 T1 is equal to T times 1 plus M1 C1 divided by M2 C2. And I can see that the temperature T then becomes, if I multiply both sides by M2 C2, it will be M2 C2 T2. So let's multiply both sides by M2 C2. M2 C2 T2 plus M1 C1 T1 divided by M1 C1 plus M2 C2, because this will disappear and I will have an M2 C2 here. Okay, so that's temperature T. Now, if I substitute this to energy conservation equation, so let's substitute to energy conservation equation, I will obtain what was the energy conservation equation, M1 C1 T minus T1. So that's going to be M1 C1 T minus T1. For T, I substitute M2 C2 T2 plus M1 C1 T1 divided by M1 C1 plus M2 C2 T minus T1 is equal to M2 C2 T2 minus T prime. So that was our energy conservation equation. Okay, now what I'm going to do is solve for T prime. Now, if I look at this expression, you can see that I will obtain M1 C1 M2C2 times T2, multiplying it with this one, and then I will have plus M1 square C1 square T1, and then I will have minus, if I multiply this with T1, it's going to be M1 C1 T1, but there's another M1 C1, so M1 square C1 square T1 minus M2 C2 T1 multiplied with M1 C1 minus M1 C1 M2 C2 T1. You can see I have obtained the same terms here, M1 square C1 square T1, so they will disappear. Okay, and this must be equal to, because I'm taking the common denominator, so I will multiply this side also with this term, so I will obtain M1 C1 M2 C2 T2, multiplying it with this term here, and then plus M2 C2 squared M2 squared C2 squared T2 minus M1 C1 M2 C2 T prime, and then minus M2 square C2 square T prime. So all I'm doing is getting the same denominator on this side and this side. So in other words, I'm multiplying this equation with M1 C1 plus M2 C2, and that gives me this result, and the denominators are the same, so they will cancel. Now I can see that I have the same term M1 C1 M2 C2 T2 here and on the right hand side, so they will cancel. And now I can write the rest. So minus M1 C1 M2 C2 T1, okay, minus M1 C1 M2 C2 T1 must be equal to what is left on the right hand side, M2 C2 square T2, M2 C2 M2 square C2 square T2 minus M1 C1 M2 C2 and M2 C2 M2 square C2 square, so minus T prime parentheses M2 square C2 square plus M1 C1 M2 C2. Now I'm going to take this equation and multiply it with 1 over M2 C2, and this will allow me to isolate T prime. So I take this to the left hand side and this to the right hand side and divide it by M2 C2. This will give me T prime is equal to, so M2 C2 squared divided by M2 C2 will give me M2 C2 T2. Plus, this minus has become plus, M2 C2 has disappeared, M1 C1 T1 divided by the parentheses here, M2 C2 square becomes M2 C2, and M1 C1 is the next term because M2 C2 disappeared from this one, and this is T prime. And what was T? T was M2 C2 T2 M1 C1 T1 divided by M1 C1 plus M2 C2. It's exactly the same result here, so T prime is equal to T. The maximum in the total entropy change is achieved when T prime is equal to T. So what does that mean? The condition T is equal to T prime for thermal equilibrium corresponds to the total entropy change is a maximum, which is consistent with the second law of thermodynamics. the entropy of the universe is increasing, total entropy change is maximized at the thermal equilibrium point. Okay, so we talked about two objects, mass M1, specific heat C1, temperature T1, in thermal contact with mass M2, specific heat 2, temperature T2 greater than T1. We know that heat must flow from 2 to 1 until they reach equilibrium. The temperature of the first object increases from T1 to T, the second object decreases T2 to T prime. The entropy increase of the system and the energy conservation requirement, the entropy change integral from T1 to T, M1C1 dt over T is M1C1 natural log T over T1. Entropy change T2 to T prime is M2C2 dt over T, M2C2 natural logarithm T prime over T2. And we add them up to get the total entropy change. The heat exchange between the two, heat added to the first one, is M1C1 delta T1, T minus T1, M2C2 delta T2, T prime minus T2. This is heat added to 2, but heat added to 1 should be equal to heat released by 2. So we have to multiply it by a minus sign. This becomes T2 minus T prime. So we have obtained the relationship suggested by the problem statement. And then we write entropy as a function of T and show that its maximum if T is equal to T prime, which is the condition for thermodynamic equilibrium. So in order to do that, first I wanted to obtain T prime over T2 using the equation of energy conservation. So I have divided this equation, energy conservation equation, by M2C2. So this gives me M1C1 over M2C2 T minus T1 minus T2, if I take this to the left hand side, equals minus T prime. So T prime can be written in terms of T with this equation. And T prime over T2, which is what appears in the entropy relation, is 1 minus M1C1 M2C2 divided by M2C2 T minus T1 over T2. We substitute that to the entropy and take the derivative with respect to temperature and set it equal to 0. After some manipulation, we find that this implies T can be written in terms of T1 and T2 as M2C2 T2 plus M1C1 T1 divided by M1C1 plus M2C2. If we substitute this result to the energy conservation equation for T and multiply the equation by M1C1 plus M2C2, we obtain T prime is equal to also M2C2 T2 plus M1C1 T1 divided by M1C1 plus M2C2, which is equal to T. So indeed, T prime is equal to T when the entropy change is maximum, which is consistent with the second law of thermodynamics.